It's Paul again with a short script about how to use the implicit function theorem to calculate approximate changes in the passive variables when you make changes in the active variables. I'm going to do two cases in an attempt to convince you that the same idea will work in any number of dimensions. We need to be able to calculate some derivatives, so I'm loading the numDeriv library. And let's start with a situation where n equals 3, we have three variables, and n minus k equals 1, we have one constraint. So we're going to end up with a two-dimensional manifold, as you will learn later on. In order to take derivatives, I need to specify my function as a function of a single vector. So instead of x cubed, I use v sub 1 cubed. Instead of 3xy, I use 3 times v sub 1 times v sub 2, and so on. And just as a matter of general principle, instead of setting this equal to 10, I subtract 10 from what I have, so I have a function whose value has to be 0. I've rigged this so I know one set of values that solves this equation, namely x equals 2, y equals 1, z equals 2. I checked that by evaluating f on v0. And now what the implicit function theorem says is that if I make changes in the active variables y and z, then this function will implicitly define the passive variable in terms of those, and I can calculate the derivative of this implicitly defined function. So here's the recipe. I calculate the Jacobian matrix, or if you prefer, the gradient of the function f. There it is. It's got three components, 13, 2, and 8. And now I split off a square matrix on the left, A. That's just a matrix with one entry, 13. And what's left over is the matrix B, which contains the 2 and 8. And the implicit function theorem says the derivative of the implicitly defined function g is A inverse multiplied by B. So let's split the matrix up. To get dg, what I have to do is take B, which is the second and third components of df, and multiply by A inverse, but that's just dividing by the number, the first component of df. And there's my derivative of the function g. How do we use it? Well, suppose we increase y to 1.05, decrease z to 1.97. In other words, the increment is y is up by 0.05, z is down by 0.03. The new value of v is the old value, v0, plus a vector whose first component is increased by the change in x. That's the derivative of the function g acting on h, and whose second and third components are changed by h. That's the new vector v. Y and z are changed as advertised, and the implicit function theorem says we need to increase x to 2.01 and change, and when I evaluate f, I see we've done pretty well. Now the amazing thing is the same thing works even if we have more than one constraint. So now we've got a pair of functions. So this function returns a first component that starts out as v sub 1 squared times v2 for x squared times y, and so on. And the second component, which starts xyz in the conventional form, starts out v1 times v2 times v3. There's my function. And in this case, I've chosen a function so that 1, 2, 3 is a solution, and I check that. Now we have only one active variable, z, because we've used two constraints, and therefore we can define x and y implicitly as a function of z, and we do things exactly the same way. We calculate the derivative of the function f. This time it's a matrix. I have to use the Jacobian function. There it is. It's got 3 columns and 2 rows, and I have ordered the variables. It isn't really tricky here. so that the first two columns are linearly independent, so I can split it up into A and B, which I can cleverly do in R by using the selected columns after the comma. So there's A and B. I have to invert A by using the solve function. The derivative of G, again, is A inverse times V. And if I now increment Z by 3.14, my new value of V is V0 plus the increment, where I have calculated the increment in the first component by using the implicit function theorem, and the second two components are just H, and there are my new values. I have had to decrease X and Y a little bit, and when I plug in f of V, again I get something pretty close to 0, and I am done.